All right, next we'll talk about subatomic particles. We mentioned them in the last presentation. So protons and neutrons are located in the nucleus of the atom, which is small, and most of the mass of the atom is due to the nucleus. There can be a variable number of neutrons for the same number of protons. That's where isotopes come in. Isotopes have different number of protons, but they have a different number of neutrons, meaning that the atoms have slightly different masses. The electrons are located outside the nucleus, and most of the volume of the atom is due to the electrons. Remember, in the previous presentation, we said the Rutherford atom was mostly empty space. That mostly empty space has sparsely populated electrons, but that's it. Atoms that come close to that very dense nucleus, alpha particles are positively charged, so they'll be repelled by the nucleus of the atom, or they'll pass through undeflected, or they'll come and bounce off and be deflected at a high angle. So these are the subatomic particles and their symbols. Elements always start with a capital letter, but the symbols for subatomic particles are always lowercase, so that you can tell which one's which. So we have the proton, lowercase p positive is its symbol, mass about 1 atomic mass unit, charge of +1 atomic charge units. The neutron, lowercase n is the symbol, still about 1 atomic mass unit, but no charge whatsoever. It's uncharged. You don't really need masses this precise for most applications, so by and large, we'll round those two masses off to just 1. The electron has a lowercase e as its symbol, and you notice the charge for the proton and the electron are on the upper right-hand side. It has a very small mass. A lot of times we'll just round that down and treat the electron as it's more or less massless, and we'll use the mass of the nucleus as the mass of the atom. And it carries a -1 charge. The atomic number is equal to the number of protons in the nucleus. The atomic number is sometimes given the symbol Z. On the periodic chart, Z is the uppermost number in the elements box. H.G.J. Moseley realized that the atomic number determines elements, so it's actually the number of protons that determines which element it is. Change the number of protons, you change which element it is you're talking about. The electrons and the neutrons can vary, but the protons cannot if you're going to keep the same element. And so that gets a symbol of Z. So your typical atomic chart square, this is for carbon, has an atomic number 6, which means carbon has 6 protons. You see the symbol in the middle, capital C. The average atomic mass of 12.01 is in the bottom. We'll talk about how to calculate that a little later. James Chadwick also determined that there was a neutral particle, which ends up being called neutrons, as a result of alpha scattering particles on beryllium films. He's considered the discoverer of the neutrons. So that gives us all 3 subatomic particles and how they were discovered. Let's work on how to figure out each isotope then. Mass number is given a symbol A. A is the number of protons and neutrons added together. If Z is the proton number and we say capital N is the neutron number, then A equals Z plus N. So a mass number equals the number of protons plus the number of neutrons. And that will help us identify each individual isotope. The common symbolism is we'll write for some generic element E, we'll write A over Z next to the atomic symbol on the left to indicate which element it is and which isotope it is we're talking about. There's some different ways to indicate each isotope. In this table, there's our carbon-12 isotope. It can be abbreviated with just the 12 because we can look on the periodic chart and get that 6. And so that can be left to be understood. If we want to say it verbally or in words in a sentence, we say carbon-12 because that's the need to know information, which element it is I'm talking about, dash, and then what's the mass number. You can do it similarly for these elements in the table. Phosphorus, a mass of 31, 15 protons. We can leave the 15 off to indicate phosphorus 31 in an abbreviated format, and then we could just say phosphorus 31. Nickel with a mass of 58, 28 protons. We can eliminate the 28 from the notation to abbreviate it, or we could just say nickel 58. So remember, the isotopes are atoms of the same element, but they have different neutrons, therefore they have different mass numbers. But they're the same element because they have the same number of protons. For example, this is the isotopic abundance of neon. Most neon is in the mass of 20, about 90.48%. There's a trace amount at 0.27%, and then the rest of it, 9.25%, is a mass of 22. What makes this example interesting is they used to think only neon had 2 isotopes, but then as these techniques that we do in lab, in this case mass spectrometry, got more precise, the limit of detection got lower, and all of a sudden, hey, there's an extra isotope of neon that we didn't know about before. So here are the isotopes of neon. They all have 10 protons, but they're going to have different mass numbers. You see 10 plus 10 is 20. 10 plus 11 is 21. 10 plus 12 is 22. And so there's different numbers of neutrons giving us different masses for each neon isotope. The number of electrons in each case, since I haven't indicated any charge yet, would end up being 10. And if a substance is neutral, the number of protons and the number of electrons will be the same. What about the case where they aren't the same? For example, when a molecule loses electrons, it becomes positively charged. If a sodium atom loses an electron, it becomes sodium with a +1 charge. In this case, I wrote the 1, but inexplicitly, but you don't have to, and usually you don't. But here I'm doing it for emphasis. Positively charged ions are called cations. When an atom or molecule gains electrons, it becomes negative charged. For example, if a chlorine atom gains an electron, it becomes chloride, chlorine with a -1 charge. Again, that 1 can be dropped and you can just do the sign. We call those anions. And the atom or molecule can lose more than 1 electron. But if the charge is 1, we tend to omit the 1 and say Na plus or Cl minus. Here's an example. We're going to determine the number of protons, neutrons, and electrons in each of the following atoms. So we got oxygen with a mass of 16, uranium with a mass of 238, chlorine with a mass of 35, but it's carrying a -1 charge. And then we got silver with a mass of 108, and it's carrying a +1 charge. So we're going to take each of those in turn and determine the number of protons, neutrons, and electrons. All right, let's look at this problem where we're trying to determine the number of protons, neutrons, and electrons in each of these isotopes. And so if we look at oxygen 16, remember, this is your A, and this is your Z. So we can tell since that Z number is equal to the atomic number or the number of protons, got 8 protons. Now remember, the neutrons plus the protons equals this, so it's going to be 16 minus 8, or 8 neutrons. Now, I haven't indicated any charge over here, so it'd be the same as the protons, so are 8 electrons. For the next one, it's a little tougher. Bottom protons is still 92. Neutrons is going to be 238 minus 92, or 146. And then the electrons will be the same as the protons at 92. Now for the chlorine, protons 17, neutrons will be 35 minus 17, or 18. The electrons, now I'm showing a charge over here, so I'm going to have to adjust that. So it's going to be the original 17. Now, if I have a negative charge, that means I added electrons. So that means I'm going to add 1 for the negative charge, and I'm going to have 18 electrons. If it was minus 2, I'd add 2. Now for silver 108, number of protons is 47, because that's the bottom. Neutrons will be 108 minus 47, which is 61. And then the electrons will be based on the number of protons, so 47. But now I've got a positive 1 charge, so I'm going to take 1 electron away because electrons are negative. I need more protons than electrons to get a positive charge, so that will give me 46. And that would be the number of subatomic particles in each of those.